Hello everyone, my name is Eduardo Quiñones, and today I'm going to present the AMPERE European project coordinated by the Barcelona Supercomputing Center and participated by the academic partners ISEP, Scuola Superiore Sant'Anna and ETH Zurich, and by the industrial partners Cisco, Thales, Bosch, and Evidence. The AMPERE project is an acronym that stands for a model-driven development framework for highly parallel and energy-efficient computation supporting multi-criteria optimization. So the motivation of the AMPERE project stands for the challenges of developing advanced cyber-physical systems. This type of systems are traditionally built using a model-driven engineering approach in which the system is defined by identifying different functionalities and the relationship existing among them, as well as the different functional or non-functional requirements of the different components. This way of describing the systems allows to formally verify the different functional and not functional requirements, such as safety, real-time, security, resiliency, etc., etc. And it's also said that this type of development processes follows a correct by construction paradigm in which the description of the system is then automatically transformed to the source code targeting the computing platform. Unfortunately, this type of transformations is suitable only for a single core execution and has very limited support for multi-core execution. And so when we want to provide more performance to this type of cyber-physical systems, what we need is to use parallel execution that are provided by parallel architectures. And in this type of architectures, the use of parallel programming models are mandatory from a software productivity point of view from three different angles. We want parallel programming models to enhance the programmability, in which allows to represent the parallel execution of your programs by having all the hardware complexities of the underlying platform. We also want to use parallel programming models in order to provide portability. So the same system can execute, the same parallel code can execute in different hardware platforms, and as well as performance. We want the underlying runtime to being able to exploit all the parallel capabilities of the hardware. And parallel programming models are especially efficient when considering heterogeneous computing in order to manage the execution among the different hardware accelerators for an energy efficient execution. However, there is a gap between the way cyber-physical systems are currently developed and the way parallel programming models are currently exploited by means of parallel programming models. And so what the AMPERE project is intended to do is to bridge this gap between model-driven engineering and parallel programming models. And we are envisioning to do this, the project is envisioning to do this through three different angles. So the first one is we want to investigate on synthesis methods that are capable of efficiently efficiently transforming the description of the system into efficient parallel source code, while keeping all the non-functional requirements of the system included there, as well as providing composability guarantees, We also, in the project, we also aim to research on new parallel runtime frameworks that are capable of guaranteeing not only the system correctness from a functional point of view, but also from a non-functional point of view as required by cyber-physical systems, while exploiting the performance capabilities of parallel architectures. And last but not last, we also intend to integrate these parallel frameworks into model-driven into current model-driven engineering frameworks used in the development of cyber-physical systems. And so how are we going to do this? So let's dig a bit more into how the AMPERE project is envisioning to do this. So in the project, we are focusing on three model-driven approaches. Autosar and Amalthea are used in automotive, and Capella is used in the railway industry. And so the objective is based on the representation of the system with these three model-driven approaches. We are intended to extract all the information of the system, including which are the computing elements, what is the communication existing about between these different computing elements, what are the timing characteristics, what are the safety requirements, etc., etc. And our intention is to research on a model transformation engine that is capable to transform this representation, this system representation, to a parallel programming model by first identifying what are the different parallel entities, what are the different synchronization dependencies existing among them, as well as the data attributes, and then transform this to actual parallel programming models like OpenMP, OpenCL, CUDA, etc., etc. In the project, these parallel programming models relies on runtimes that are in charge of controlling the parallel execution. And so we are also intended to research on how these runtimes needs to be implemented. So all the requirements imposed by the system are guaranteed at the execution time. And of course, we want to integrate all this framework into model-driven engineering frameworks currently used in the cyber-physical industry. And the way we are going to do this is by developing a novel software architecture that is described on the left side of the image. So it is composed of two main blocks. The block that is related to the system development, and the block that is related to the execution of this system. And this software architecture is going to being able to capture all the description of the system at component and communication level, as well as including the non-functional requirements. This software architecture is going to have the capability of fulfilling these non-functional requirements. And more precisely, we are going to focus on energy efficiency, safety, cybersecurity, real-time response, resiliency, and fault tolerance. And of course, the objective of the software architecture is to make an efficient use of the parallel architectures so we can increase the performance of the cyber-physical systems. And a key objective of this software architecture is to increase the productivity in the development of the advanced cyber-physical systems from three different aspects. From a programmability point of view, we want to facilitate the development of new functionalities in cyber-physical systems, we want also to ensure portability and scalability. So if I replace the different computing elements with new hardware architectures, more powerful hardware architectures, the system is going to still working and the performance is going to be improved. And of course, the software architecture also needs to provide performance. This software architecture, the components of the software architecture are not intended to be developed from scratch, but we are going to use well-known tools already used for the development of embedded systems and high-performance systems, from a domain-specific modeling language, from parallel programming models, from compilers and hardware synthesis tools, runtime libraries, operating systems, and hypervisors. Although in this project, we are going to pay special attention on the languages used to describe the system and the parallel programming models used to program the parallel architectures. So from a workflow point of view, the way the software architecture is going to work, the first thing we are going to do is to have a representation of the system, including the description of the components and communication, the functional and not functional requirements, as well as a description of the platform, including what are the acceleration devices, the cores, the clusters, the memory model, etc., etc. Then with this, we are going to be able to generate a transformation that is going to take into account the different non-functional requirements, and a compiler phase that is going to check the correctness of this transformation, as well as defining providing a refined parallel structure, addressing OpenMP, CUDA graphs, OpenCL, etc., etc. And we are going to provide a first resource allocation of the computation on the different parallel execution units of the underlying platform. And then at execution time, our runtime framework is going to constantly monitor the execution of the system, so we can, on one side, enhance the system description and the platform description from a profiling point of view, as well as being able to dynamically reallocate the resources to achieve a better performance. As I said before, the project is targeting real cyber-physical systems, and concretely we are focusing on the railway and the automotive domain. With respect to the railway, we are going to test the software architecture to implement an obstacle detection and avoidance systems for tramways. And in case of the automotive domain, the software architecture is going to be used to implement a predictive cruise control that extends the capabilities of current adaptive cruise controls, with the objective of improving the fuel efficiency of the vehicle. So to conclude my talk, the AMPERE project aims to bridge the gap between the model-driven engineering methods and the parallel programming models used in the most advanced parallel architecture. And the way we are going to bridge this gap is by providing first a development framework for implementing cyber-physical systems targeting parallel heterogeneous architectures. We are going to provide an execution framework that is capable to exploit the performance capabilities of parallel heterogeneous architectures, fulfilling the non-functional requirements of the system. And we are going to integrate all the Ampere solutions into two relevant industrial frameworks, that is the automotive and the railway, that requires high performance computing. So thank you very much for listening this talk, and I encourage you to stay connected to the Ampere news that you will find in LinkedIn, in Twitter, and in the webpage of the project. Thank you very much.